In this video, I'm going to talk a little bit about our modern understanding of the atom and how our ideas have sort of evolved since talking about the Bohr's model. So remember Bohr had these specific energy levels and he had nice circular orbits for the electrons and they were going around the nucleus in these nice perfect circular orbits. Well, our modern atomic theory actually doesn't have anything that looks like that. It's quite a bit different. And so what it's based on is these two fellows, Schrodinger and de Broglie, were really incredible physicists. They were incredible mathematicians, and they came up with this mathematical explanation for how the electron would behave within an atom. They thought, okay, there's this behavior of the electron where it behaves sort of like a particle and kind of like a wave, sort of like light does. All right, and they came up with these mathematical relationships for how it would work. And the Bohr model, while it was limited to working with hydrogen, he found that this worked out for a bunch of different atoms, and so it predicted the way that atoms behaved. And so, based on the complicated math that Schrodinger and de Broglie were going through, they found this new model, which they call the wave mechanical model, and it's based on really complicated physical and mathematical relationships that predict the probable locations of electrons, and I'll kind of keep hitting that and talk about what that means and how things go for here. So here are kind of the parts of it. First of all, there are these things that are called orbitals. The word orbital sounds like the word orbit, but I want to make sure that you know that an orbital is not an orbit. An orbital is a region in space where an electron probably would be, and it's based on this complicated mathematical prediction. The electrons don't simply go in a circle around the nucleus. They have actually really complicated movement. All right, but there are these regions in space that we predict where the electrons are more likely to exist, and that's basically how this model works. The other thing here is we have energy levels. Sort of similar to Bohr, there are energy levels here, but the energy levels are not exactly the same because they're not related to the perfect circular orbits. There are a total of 7 energy levels. We go 1 through 7. They're sort of related to the rows on the periodic table, which if you look at the Electron Hotel video, we talk a little bit about the rows on the periodic table and how they line up with the S blocks and the P blocks and the D blocks and the F blocks and things like that. And what this means for the energy levels, basically the innermost energy level, the lowest energy one is called n equals 1, and the highest energy level is n equals 7. All right, and they go up that way. For sublevels, there are 4 different sublevels. There's S, P, D, and F. All right, and you don't have to remember exactly what these means, but that stands for sharp, principal, diffuse, and fundamental. And so I won't ask you that really ever on a test, but that's what the S, the P, the D, and the F stand for. It doesn't actually really even mean anything to me. I don't understand how S is sharp and P is principal, but it's what it was based on whenever whoever was naming them came up with that. So I'm going to go through some things to remember about these different sublevels now. I'm going to talk about this a little bit more in depth. So there are 4 of them, remember. They go here, S, P, D, and F. That's in order of lowest to highest energy. All right, so we're going to fill an S sublevel before we fill a P sublevel because it's just a more energetically favorable place to put electrons. The shapes of these can be pretty strange. The first one's pretty simple actually. S, if you remember S is sphere. It's actually, as I said, it's called sharp, but if you remember S is sphere, that might be a mnemonic that you can use to remember this. So it's a region in space, remember, where electrons are probably located, and so what we've got here for the s orbital is the region in space is the shape of a sphere. What I have pictured here is the 1s orbital, the 2s orbital, and the 3s orbital. You'll notice that they get bigger as we go out, and so this is 3 different energy levels. First energy level, s orbital. Second energy level, s orbital. Third energy level, s orbital. And so it gets bigger as you go through here. The P has a little bit of a different shape. What it looks like is it looks kind of like it says an infinity symbol or like a dumbbell shape. Or I think about it, if you took a balloon and you like twisted it in half or something like that, it has this sort of double lobed shape. So within an energy level, this is a little bit different than what we saw before, because for the S, we are looking at 3 different energy levels. This is 1s, 2s, and 3s. Within any one energy level, there's just the one sphere. However, with the P, what I'm showing you here is actually 3 orbitals within the same energy level. One is along the x-axis, one is along the y-axis, the other one is along the z-axis. If you put them all together, they look like this. So this isn't a 4th one, it's just the other 3 put together into, so you can kind of see how they relate to one another. But within one p sublevel, there are all 3 of these orbitals. And so that's why there are 3 boxes when we do the electron configuration for something that's in a p orbital. There are 3 boxes, or it's why in the electron analogy, we had a party room and there were 3 bunk beds. It stands for the 3 orbitals within the p sublevel. So S only has 1 orbital within its sublevel, and we'll talk about that in just a second again. D gets a little bit crazier, so we've got this sort of cloverleaf shape. Alright, so there are 4 of them that are sort of in a cloverleaf shape, and then we have this last one here, which I remember it as sort of like a double pacifier, which is kind of a weird thought. I don't exactly know how that would work. If you had 2 babies and they were both using one end of this, I think it would look a little weird, but whatever. I think the shape double pacifier makes sense to me, and that's kind of what I think of when I think of that. So cloverleaf or double pacifier. Notice there are 5 different orbitals here, so they've got different names based on the planes that they're lined up with. This one is lined up with the YZ plane. This one is lined up with the XZ plane. This one is lined up with the XY plane. This one is kind of rotated on the Y and X plane. And then this one is completely different. All right, so so these are the different shapes that we get here. And again, these shapes are based on that complicated math that Schrodinger and de Broglie were coming up with. So it's not just out of nowhere, but it's really complicated relationships between like the attraction to the nucleus, because the electrons are negatively charged and the protons of the nucleus are positively charged, and those would be attracted, and also the way that the electron behaves sort of like a wave. It predicts these regions in space where the electron most probably would occupy given its position within these sublevels. Alright, so each of those different shapes, as I said, represents an orbital. S, there's just the sphere. P, we had those 3 dumbbells. D, we had 4 of the clovers, and then we had that 1 double pacifier shape. So the number of orbitals that they had, the number of different shapes are listed there. And then F has 7. I didn't show you that. If you want to Google what the F orbital shapes are, you can find a picture of that. There are 7 of them. They look pretty weird too. So now, inside each orbital, 2 electrons fit, and one of them will have will be spinning one direction, and another one will be spinning another direction. And I'll kind of talk about that here in just a moment, what that means. But in each orbital, you kind of get the 2 electrons. So that means in the P sublevel, if you've got 3 different shapes, 3 different dumbbell shapes, then we have 6 electrons that can fit in there. In the D, there are 10 electrons that can fit, and there are 14 in the F. So notice if you just take the number of orbitals and multiply them by 2, because 2 electrons fit in each orbital, then you get the number of electrons that can fit within that sublevel. Alrighty, so just summarizing this, there are these principal energy levels. Within the first energy level, there's actually only the S sublevel, because if you remember back with the electron hotel analogy, if you take this first row, you only have the S block. Alright, you go across here to the P's, and there's nothing over there. So for the first energy level, there's only an S sublevel. For the second energy level, we have the S block here, these 2 atoms, and then the P block over here. So S and P for energy level 2. For energy level 3, we have S, P, and D. So 3S is third row S block. Alright, 3P is third row P block. That's these ones in here. And then 3D is actually, remember, we drop down 1 for D's. So you go into this 4th row. But these ones here in the D block are called 3D. Alright, they fit here. And then in the fourth energy level, there are S, P, D, and F sublevels. Okay, when we write the electron configuration, we write these things like 1s2, 2s2, 2p6, 3s2, etc., etc. All right, and I want to clarify kind of what that means. The number in front there is the energy level. So what this is saying is first energy level and third energy level. All right, the letters there then are the sublevels. So when we say 1s2, we're saying first energy level S sublevel, and then third energy level D sublevel. And then this is the number of electrons that exist within that sublevel. So 1s2, 2 electrons in the 1s sublevel. All right, 10 electrons in the 3D sublevel. This kind of just shows you the shapes and how they fit together. So when you put electrons in, as I said, the first place that they go is the first energy level S orbital. So that's called 1s. That is this small sphere that's right here going around the nucleus. So the first electrons go into this small central sphere called the 1s orbital, and then they go into 2s after that. 2s is this larger sphere. All right, and then after that, you're putting them into 2p, which, remember, there are 3 2p orbitals. All right, there are 3 2p orbitals within the second energy level, p sublevel. You get the one along each axis, so we get 6 electrons that we can put in here. And then after you fill up the 2p sublevel, we jump out and we go through 3s. That's this even larger sphere. All right, so as you're putting electrons in, this represents the shape of the probable region in space that the electrons are going to occupy, and then it's just getting bigger and bigger as we add more and more electrons on. Okay, so those 3 guys from the Electron Hotel analogy that I talked about, they're actual scientists. They have real rules. One of them is this guy named Pauli. He has something called the Pauli exclusion principle. And what it says is that there are 2 electrons that fit in each orbital. All right, one of them has a spin in one direction and one of them has a spin in the other direction. And so when I say spin, I'm talking about like the Earth on its axis. Okay, so electrons spin in the atom, and as they spin, they create a magnetic field. If they're spinning one way, the magnetic field is up. If they're spinning the other way, the magnetic field is down. All right, and it has to do with the magnetic field that's created as the electron spins. Within an orbital, you have one electron spinning one way and the other electron spins the other way. All right, you cannot have 2 electrons in the same orbital spinning the same direction, and this is why it's called the Pauli exclusion principle. So just like you can't have top or bottom bottom is what this is saying. Within an orbital, you have one going up and one going down. Okay, some other things here. It says there are 2 electrons per orbital. So if you remember, if we talk about the sublevels and how many orbitals they have, S sublevel has 1 orbital, so it can hold 2 electrons. P sublevel has 3 orbitals, so it holds 6 electrons. D sublevel has 5 orbitals, so it can hold 10 electrons. And F has 6 orbitals, so it can hold 14 electrons. So generally speaking, paired electrons, if we can have an orbital that's filled, it tends to be more stable than an orbital that is unfilled. All right, so generally speaking, the most stable things have filled orbitals, and we'll talk a little bit about this actually when we go into talking about our unit on the periodic table. But generally speaking, we want filled orbitals here. The Aufbau principle, this was the guy who said that he wanted to fill the lowest levels of the hotel first. Basically what this says is you're going to fill the lowest energy sublevels first. So we start by filling 1s. All right, and then after that we fill 2s, and then we fill 2p, and then 3s, and then we fill 3p and 4s, and then 3d, 4p, 5s. So you can see this order and how it goes. As you go through this, you can kind of see some patterns. In the first energy level, we only have an S sublevel, so it's just 1s. In the second energy level, we have S and P. In the third energy level, we have S, P, D. And then we just say SPDF, SPDF, SPDF for the other ones. And then again, I kind of prefer just to look at the periodic table to think about the order that they go in, because if you just read left to right, top to bottom, and remember that way, it goes through the orbitals in this way. But this is just a kind of a different way that you can approach trying to remember the order that you fill the sublevels in. Either way, as I said, I like looking at the periodic table better, but this is another mnemonic device for how you might remember this. All right, the last one here, we have Hund's rule. Basically what it's saying is within a sublevel, electrons are going to spread themselves out. And so within the P sublevel, this is the whole idea that you have up, 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 and then down, down, down. You don't have an up and a down together. This is sometimes called the bus seat rule. And here's the idea. If you went and you got on a bus and there was no one else on the bus, or like there was one other person, right? You wouldn't go sit down right next to that person. You'd find another seat. And so the idea is if you're filling electrons in a sublevel, right, and there are, say, in the P sublevel there are 3 orbitals, if you're filling the electrons in, you're going to have up, 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 okay, so they're going to separate themselves into these different orbitals, and then you'll go down, down, down. All right, so that is that in terms of my rules for the modern model of the electron. Try and get to know these different rules, and I won't ask you probably to recognize the name of the rule, but I want you to know what the rule says, so be able to apply this rule when you're doing problems.